problem. Problem C. Let's try this one last time. Again, we've got a huge equation with n's in it. We want to prove it's true using mathematical induction. So step 1, as always, tells us to plug in 1 and make sure it's true for 1. If it's not true for 1, we don't even need to go any further. So let's plug in our 1. That means we'll only get to that first term, the 1 cubed. Then we'll plug in a 1 on the right-hand side too for all of our n's. Well, notice, according to the order of operations, we'll always do what's inside your parentheses first. So the 1 plus 1 will give you 2. And then what else do we have? Next, the order of operations will tell us to take care of both of your exponents. Well, let's see. That first one, 1 squared, is 1. And then we also have a 2 squared, which is 4 on top of the right-hand side. Then continuing right along, we have a 1 times 4 on top, which is 4. Which then, if I go ahead and do the math, 4 divided by 4, does that equal 1? It sure does. 4 divided by 4 is 1, so yes, this does work out. You get a true statement where both sides are the same. So this does mean it's true if n equals 1. Step 1 is done. Now, again, what does mathematical induction also tell you have to do? Well, now you have to look at the kth term. So we'll look at the kth term, plugging in a k wherever there's an n. And remember, mathematical induction says, okay, you're going to take that equation and assume it is definitely true. Assume it is fact. So let's start that and assume it is true, whether you believe it or not. Now let's look at the same equation, but going up one term past that. We have to look at the k plus 1th term. So let's look at the k plus 1th term. Well, we'd still do the 1 cubed, 2 cubed, all the way up to k cubed, but we'd go one number past that, one term past that to k plus 1 cubed. On the right-hand side, instead of a k, we'd have a k plus 1 squared. And on the second piece where the k was, we'd also replace that with a k plus 1. Well, there's actually quite a bit of math to do here. First, though, let's use what we assumed was true. Let's use our starred equation, which says that if we have the left-hand side, the 1 cubed, all the way up to k cubed, add it up, we can use that star equation to replace that with the other side. The k squared times 1 plus k squared over 4. So we'll just make a swap. So we're just going to replace the left-hand side with the right-hand side. Everything else, notice, has stayed the same. We kept the k plus 1 cubed. On the right-hand side, we just did only one minor thing, which is we have a plus 1 and a plus 1 on the right-hand side inside of all those parentheses, and we turn that into a plus 2. So we really didn't do much on the right-hand side. Continuing along, what do we notice on that left-hand side compared to the right-hand side? Well, on the right-hand side, we have one big fraction. On the left-hand side, we've got 2 pieces, only one of which is a fraction. So what we would like to do is turn that second piece, that k plus 1 cubed, into a fraction as well. Now, automatically, what does it have on its denominator if you don't see anything as a 1? So what we'd like to do is get the same denominator as the first fraction. We would like to force a denominator of 4. Well, how am I going to get this 1 to turn into a 4? Well, I've got to multiply the bottom and the top by 4 to get that common denominator of 4. So that's what I did. I multiplied the top and the bottom by 4 to get a common denominator of 4. Now that they match up, I've got a common denominator of 4. I can just add and subtract normally. So I'm just going to put them as one big fraction. The first fraction had the k squared times k plus 1 squared. That hasn't changed. And the second fraction had the, let's see, 4 times k plus 1 cubed. That's still there. It's just they're all under the same fraction and they're now all over 4. We're getting close. We have one fraction on the left and one fraction on the right, but they don't look the same yet. They're getting closer. Notice. What do I notice now? Well, if I look at my fraction here on this line, on the left-hand side, notice we've got a k plus 1 cubed here and a k plus 1 squared. So each of the two pieces on top of our left-hand side both have a k plus 1. So what this is called is a greatest common factor. How many of these k plus 1s can I pull out of both of these pieces? Well, I can factor out a k plus 1 squared. So I can pull out 2 of them. So that's what I'm going to do is I can pull out a k plus 1 squared. Remember, whatever's left over from factoring will land in a set of parentheses. Well, what's left over from the first piece, if you pull out the k plus 1 squared, is just the k squared. So you'll notice that that's what you see right off the bat, is the k squared. Now on the second piece, it's a little bit more complicated. What's left over is your 4 that you already had. Problem. You pulled out 2 of the k plus 1s. There were 3, so you still have a leftover k plus 1 there. It's still there. But we'll put it down so that we don't lose it. Now, we're almost there. We're almost home free. Our last part is that we need to simplify what's inside of these parentheses here, inside of these red parentheses on that top of the fraction on the left. So we want to simplify that. Well, the first thing that we can do is distribute out the 4. That will get us a 4k plus 4. That's what we see down here. Getting there. Now the question is, what we've got there inside of those red parentheses, the k squared plus 4k plus 4, can it be factored? And yes, it can. What 2 factors of 4 add up to 4 is a 2 and a 2. So that means it will factor out as a perfect square, a k plus 2 and a k plus 2, which is the same as what we have on the other side. A k plus 2 times a k plus 2 is a k plus 2 squared. That means that these two sides are the same. So what did we just show? We showed it was true for k plus 1 by assuming it was true for just k, which is all you need to do. So what does this mean? This means that mathematical induction showed that this statement is true for any n that you could possibly think of. Now, when you do your homework on this in my math lab, they can't have you write out these proofs in detail. So they'll have you fill in a couple steps here and there, giving you hints along the way to kind of force you through the proof the way that they want you to do it. But they will lead you and kind of tell you what they're expecting from you. The goal is for you to understand the concept here. If you wanted to see more information on proofs and things like this, these specific mathematical induction proofs you would see in what's called an abstract algebra course. And you might also see them in a discrete mathematics course, which has a little bit to do with computer-based math programming type stuff.